Hi, welcome to Module 8 of Lecture 10. Now, having gone through all sorts of stuff with matrices and inverses and transposes and all that kind of stuff, multiplication, I'm going to kind of bring it together now in this module, which lists a whole bunch of properties of matrix multiplication, addition, transpose, inverse, and so on, just to give you a sense of exactly what the range of things you can do with these objects are, right? What exactly you can do with all these objects, how you manipulate them properly, how you make use of your knowledge of how to multiply them now if you have, say, more than one in a row. So that was probably very vague, so let me be explicit here. Over here we have a bunch of general, on this slide we have a bunch of general rules. I'm just going to go through one by one and show you what I mean by them. Okay, so start with the first one. So associative could be either under addition or under multiplication. Under addition, you have the fact that a plus b plus c, for matrices or vectors or whatever, is going to be a plus b plus c, so it's association under addition. It's also true for matrices under multiplication. So you can do whichever one you want first. You can associate whatever you in any order you want. Distribution under addition works too. So if I have a plus b times c, that's equal to ac plus bc. Also, I can do it backwards if I wanted and have ca plus b, which would equal ca plus cb. So that's right multiplication. This is left multiplication. But you can distribute out that just fine. That leaves commutative. Now, I've already said matrix multiplication is not commutative. So in general, AB does not equal BA for matrices. It does for vector dot products though. So A dot B equals B dot A. That's commutative. So that works just fine. And certain other things are commutative. AI equals IA, as we said before, and A inverse equals A inverse A. So certain things are commutative, but most are not. Okay, so that gives you a sense of that of the qualities that fall into that first category. Okay, let's move on to the next category. This one in red to be different. The trace. Now these aren't that important in general. A trace is not used all that often, but we still can write a couple easy ones. The trace of A plus B equals the trace of A plus the trace of B. This follows pretty much directly from this definition, just the trace of the sum of the diagonal elements. If you add two matrices, the diagonal elements are just the sum of the diagonal elements of each. So the trace should be the just you just add each one separately and then add them. It doesn't matter what order you add them in. So for instance, you could do A1 plus A22 plus B11 plus B22, which is the same thing as A11 plus B11 plus A22 plus B22, and I flipped the order here, but this is the same as this, and this is the same as that. Point is, it doesn't matter what order you add things in. That's the trace. Transpose. The trace of the transpose is the same as the trace of the matrix, again, because the diagonal doesn't change when you take a transpose. And again, this is helpful to use only square matrices. And let's see, and the trace of AB equals the trace of BA. That's true for two matrices. It's not necessarily true for any permutation of three or more matrices, but any cyclic permutation will work too. Okay, there you go. So there's a bunch of definitions for trace. So let's work on transpose. Now transpose is more interesting. We can start by using the transpose, and I'll go back to blue over here. Using this one now. So dot product, as we've kind of seen before, can be written as A transpose B. Remember that if A and B are both column vectors, A transpose makes the, so if A and B are column vectors like this, then A transpose B makes it look like that. And remember, you multiply the two things by taking this one over here, rotating it, and taking the dot product with this thing. So one way you can write A dot B is as A transpose B for two vectors. Okay, The transpose of a matrix, the transpose of that is equal to the matrix itself. If you flip it and then flip it again, you get back to where you started again, so it's its own inverse. Addition works just fine. A transpose plus B transpose. Again, if you are adding two things, you're adding each individual component with the corresponding component or element or whatever, and you flip them both, you're still adding the same exact things. So everything is fine there. So you can just take the transpose of the sum as the sum of the transposes. Multiplication is no trickier. If you take the transpose of A times B, this is going to equal B transpose A transpose. This thing comes up a bunch, so you might want to remember that. When you take the transpose of a product, you have to flip the order of multiplication. AB transpose equals B transpose A transpose. We defined earlier symmetric matrix, one in which the transpose is the same as the matrix. This is a symmetric matrix for only. And finally, you can flip. If you have A inverse transpose, that's the same thing as A transpose inverse. These things can be switched in order. Okay. There are a bunch of potentially useful transpose properties. Okay. That's that. So we'll move on now to the determinant. We'll do that in green. So we have the determinant of a transpose is the same as the determinant of the original matrix. And we keep going. The determinant of the identity is just equal to 1 because you effectively just multiply all the 1's by each other. So that gives you 1. The determinant of A times B is equal to the determinant of A times the determinant of B. This is pretty useful often. You can get directly then the determinant of the inverse of a matrix is equal to 1 over the determinant of the matrix. You can see that because the determinant of I is 1, the determinant of A inverse, is the same as the determinant of 1. I'll just do that actually. I can't really have any room here. Determinant of A inverse equals the determinant of I, which is 1. But it also equals the determinant of A times the determinant of A inverse. So you see that 1 equals the determinant of A times the determinant of A inverse. You divide both sides by determinant of A, and you get this thing down here. That's multiplication. You just need the scalar multiplication. So if you have an n by n matrix, then if you want the determinant of C times A, that's going to equal to Cn times the determinant of A. And the reason there is you just basically end up pulling out of every single term a C, and since in every case there's, for an n by n matrix, there are 3 elements in each term in the determinant. If you want to, for n elements in each term in the determinant, if you want to see that, a 2 by 2 matrix, right, the determinant is A11 times A22, so 2 things multiplied, minus A12 times A21, 2 things multiplied. For 3 by 3, you had the butterfly rule, right? That was 3 things multiplied. For an n by n matrix, you always get terms that have n things multiplied. So if you have C times A, you pull C to the n out of everything to get rid of it. So that gives you that. And that's most of it. The final one is if you have a triangular diagonal matrix, A, so A is triangular or diagonal, then it's just the product I of all diagonal elements. The reason is for a diagonal matrix, you just multiply. So you choose, so let's draw this out here. These are I's, by the way, not 1's. If I drew a diagonal matrix out, I would have A11, A22, A33, the zeros. Well, I do this. I can expand out in any one of these rows and columns. So I get the element A11 plus 0 plus 0. Now I have this submatrix over here. I expand that one out. A22 with zeros, so I have a1 times a2, 2. I can keep going for n by n and eventually get down to just the product of all diagonals. If I had something in the lower part, you might think there's a problem. However, since the upper part is 0 in that case for a lower triangular matrix, or the reverse for an upper triangular matrix, you effectively multiply all the stuff in the bottom by 0, so it all goes away anyway. So the determinants of lower triangular matrices or upper triangular matrices or diagonal matrices are just a product of the diagonal elements, so it's nice and easy relatively. So that covers the determinant. Some properties of the determinant, and finally we can do the inverse. And the inverse, first of all, the inverse of an inverse is back again. We can do the inverse of a product, which obeys the exact same order switching rule of the determinant. The inverse of AB is the inverse of B times the inverse of A. And finally, as long as C doesn't equal to 0, the inverse of CA is going to equal 1 over C times the inverse of A. And that's it. That's the entire thing. That's a whole bunch of maybe seemingly random properties of these matrix operators, but they might come in handy, and they're in the book as well. In chapter 12 at the end, there are a whole bunch of tables with all these properties, and you can always refer to them later if you want. Okay, that covers the properties of matrix operators. Now, in the very last module in this lecture, we're going to do a concrete example involving linear regression OLS. Thank you very much.